So the next topic is still in diffusion flame, but we will talk about the internal structure of the reaction zone. Then we'll talk about mixture fraction formulation and edge flame. I just put in here the general equation just as a reference. The idea is now that we want to focus on in other words, the discussion is really quite general at the moment. Not any specific configuration as I discussed in the previous lecture. So these are the general equation, right? This is the material derivative, so depending on the velocity field, which the Navier-Stokes equation are written here. And then you have the energy equation and the reaction term, and it's of course under the same isobaric assumption or quasi-isobaric assumption. Okay, so the reason I say quasi-isobaric instead of isobaric because the pressure is not totally constant. It's only constant here, but the small variation are clearly must be in the momentum equation to balance momentum. So anyway, so these are the general equation. We are going to make them dimensionless using some velocity that will characterize the flow field, and then d thermal divided by u, which is a diffusion length as a unit of length. And then here are the dimensionless form of the equation, very similar to what you have seen just in the past hour. This is the flow time, and therefore the Dam color number here is inversely proportional to the velocity. You increase the velocity, you reduce the Dam color number, and so on. Beta here, or beta naught, beta here is a little different than what I have defined before as a Zeldovich number, but in the context of diffusion flame, that's the beta I'm going to use. Essentially, it's almost like E over R divided by T stoichiometry instead of T naught. But anyway, there is, in other words, a factor here, T naught over T stoichiometry, which you see it appears here, and so the form of the exponent is different. Everything is consistent. There is really no, it's straightforward, more or less. I will use tilde for dimensional variables in this context. So this is the, maybe I should be more specific. I wrote the Arrhenius, or the exponential, by introducing this stoichiometric temperature here. And therefore, I define d by multiplying it with e, as you see, e to the minus r over t stoichiometry, okay? And the stoichiometric temperature for a given problem is known, so, okay. Just for precision, the stoichiometric temperature is the flame temperature that corresponds to complete combustion, namely the Burke-Schumann flame temperature for whatever Lewis number that you are using. Okay, it's not the adiabatic flame temperature, it's stoichiometric temperature. The discussion here follows a paper by Cheatham and myself, where what we have done, we have in fact discussed the structure of the thin reaction zone. So if this is the reaction zone, on this side there is a fuel stream, on this side there is an oxidizer stream. No, in principle, no fuel here and no oxidizer. I say in principle, in other words, there is, to order one, there is no fuel oxidizer, because as we will see, there are conditions where there is a leak of fuel and oxidizer. And the idea is that you want to introduce a coordinate system normal to and tangential to the flame surface, so the unit normal is defined here. And so all the gradient in these equations are going to be essentially the normal derivative plus a tangential gradient. And since the reaction zone is thin, then the dominant effect is going to be variation in the normal direction. So that's what, in principle, we do. But the first thing we are going to do is discuss the reaction zone of the Birch-Schumann flame. In other words, no assumption on activation energy, just that the Dam-Kohler number is large. So what you do, you stretch or you zoom on the coordinate system normal to the flame at the reaction sheet. So this is the stretching transformation. N is epsilon eta. So eta will be a coordinate that describes the boundary layer, if you like. The fuel is nearly consumed, so it's small amount. The oxidizer is nearly consumed, so it's small amount. Temperature vary a little bit from the stoichiometric temperature, so tau is the variation of temperature. And since rho times T is 1, then the density clearly will be related to this tau in this fashion. And then when you substitute into the reaction term, you get the Dam-Kohler number. You get from rho essentially the value, the stoichiometric value, from YF epsilon YF, from YO epsilon YO, and the exponent here become e to the epsilon beta tau, okay? If we don't assume anything on beta, then clearly e to the epsilon something is is approximately 1, and so the exponent doesn't appear in the reaction term. And since the major variation are going to be in the normal direction, the dominant term is diffusion. We know that that's usually the dominant fluxes. So what you get for the temperature equation is the contribution from the Laplacian, which is this, balancing the reaction term. Now, here I rewrote that expression, and since we expect a balance, then we expect that the product of all these large and small terms are order 1, which means that the small parameter epsilon is chosen to be the Dam-Kohler number to the minus 1/3. The rho s here is just to simplify the expression. It's a finite number, so it doesn't matter. So essentially, in the large Dam-Kohler number limit, the thickness of the reaction zone goes like d to the minus 1/3. And then this is the equation that is left to solve. Of course, there are similar equations that you construct for YF and YO. In fact, you can also construct, here they are, okay? And you can, when you combine them with the equation for the temperature, you have these coupling functions that are always obtained inside the reaction zone because there is no convection term that disturb you in constructing these equations. So you can solve these. These are linear equations easily to solve, and then you substitute into the equation for tau for the YF and YO to solve for it. So this is essentially what is done. I'm not showing you all the detail, but clearly solution of this is a linear function, A eta plus B. Solution of this is also a linear function, C eta plus D. And these constants are obtained by matching with the solution outside. And so you obtain exactly what they are. In particular, since the Birch-Schumann is such that there is no fuel on one side, no oxidizer on the other side, B and D are 0. So once you know this relation, you put them into the right-hand side of the equation for tau, and you get this a single nonlinear equation to solve. This equation describes essentially the structure. Physically, this is the heat conduction, this is the fuel consumption, this is the oxidizer consumption. That's what it reduced to. And the reason they get simpler because, you know, within the reaction zone, they take simpler form. Now, the matching condition are that as eta goes to negative infinity, in other words, as you approach the fuel edge, tau has to have this slope, and when you approach the oxidizer side, the slope is minus C. Remember that the temperature does something like this, And so clearly the slope here is positive and here is negative, so it just fit that picture. So this is the mathematical problem you have to solve. Of course, you have to solve it numerically. It's a boundary value problem. Typical method is like shooting method, but there are today more robust method in MATLAB, Mathematica, whatever, to solve this. But manipulating a little bit this problem, one can show that, in other words, manipulating is just making a simple transformation from eta to zeta and from tau to phi. You can show that no matter what the constant, you can always write it in this canonical form. The beauty about this is that it has no parameters, so all you have to do is to solve one time for all the structure of the Birch-Schumann solution. And so you can solve this problem. Note that the slope are plus and minus 1, and that's the equation. And so here is the solution. This is the slope that it had to reach eventually, plus 1, minus 1, and the red curve with a dashed red curve is the numerical solution. This proved that the Birch-Schumann solution always exists, and therefore the discontinuity in slopes that I was concerned about before is no longer a worry. It always can be smoothed out. Note that the Birch-Schumann solution is such that the exponential has made no contribution, the Arrhenius exponent makes no contribution to the reaction zone, and it's purely, if you like, a mixing in that thin zone. So it's not in a way satisfactory, as I said earlier, because we expect that maybe the problem described under some condition, extinction happened. And so this was discovered later, and the pioneer work in this is Amable Lignan in Spain. Lignan noticed that, or identified, even though before that Fendel, as I have told you, have solved the problem numerically, but Lignan was able to find an appropriate distinguished limit to be able to describe the structure properly. Distinguished limit in the asymptotic jargon, it means that you have two parameters, small or large, and you relate them in a certain way. In other words, sometimes it's equivalent to some similarity rules that you find, but that's the idea. So Lignan said that we have not only 3D going to infinity, but also beta goes to infinity, namely to use the idea of the activation energy large. So as I told you, the general formula, so this was the paper by Lignan in Acta Astronautica in 1974, and the more, Lignan did it for unity Lewis number, and later one of my students and myself did the problem in more generality for non-unity Lewis number. So the generalization is the following. Again, you stretch the coordinate n. This is the fuel, the oxidizer. They are small amount near the reaction zone. The temperature is a deviation of the stoichiometric temperature, and this is the density. But, and this is exactly the same line that I showed you before. In the reaction term, you get the Damkohler number, the fuel, the oxidizer, and the exponent. But now we're not neglecting this thing, we're going to retain it. And the idea is that when you obtain on the left-hand side the convective term and on the right-hand side the reaction term, you want to retain this term, so you're assuming that epsilon is the reciprocal of beta, right? So epsilon beta is 1, that's one assumption. And therefore the exponent is retained. And the second assumption is for these to balance that the Damkohler number must be such that d epsilon cube is order 1. So this is the distinguished limit that I was referring to. Now the problem is this. You have the heat conduction, you have a fuel oxidizer, but you also have a strongly temperature dependence through this exponent, and that you will see makes a huge difference. So again, this is very similar to before. The combination of temperature and fuel mass fraction and the temperature and oxidizer mass fraction can lead to linear relation. The constants are obtained by matching. And the canonical problem that you obtain after this transformation, unfortunately, doesn't depend on no parameter, but it has two parameters, but that's even good because those parameters are illuminating of what's going on. So what you have is, again, the interpretation is this is the heat conduction, this term will be the fuel consumption, the oxidizer, and the Arrhenius dependence. There are two parameters, delta and gamma, and I will talk about them in a minute. And there is also, and the boundary conditions are such after you do this transformation is that the slope are plus and minus 1. So these two parameters are important, but before I discuss them, note that when delta goes to infinity, delta to the minus third go to 0, e to the 0 is 1, and you get exactly the structure that I earlier told you, the Birken-Schumann structure. Delta will be essentially a reduced Dam-Kohler number, and so large delta should correspond really to the Birken-Schumann limit. So that's good. Okay, this I told you already. So this is what the problem, the boundary value problem that you want to solve show. Suppose that I specified gamma and delta, and I'll tell you in a few minutes what they are. So what you want is you want to find a solution that has a slope 1 here. In other words, it has to asymptote to a line parallel to this green curve. Let's say this dotted dashed green curve on one side, and then it goes through zeta and it approach the slope -1 on the other side, right? That's what the problem requires you to do. But you see, to solve, the boundary conditions are on the slope. The value at -infinity and +infinity is an outcome of the solution. So out of the solution, what you get is how much the solution deviates from this asymptote, from phi equal to zeta, right? And one can show through the simple algebraic stuff that this is exactly proportional to the amount of fuel that leaks or oxidizer that leaks. So this amount will be, if this is the fuel, it will be the oxidizer leakage, and this will be related to the fuel leakage. And so we can, and one more thing, the flame temperature clearly doesn't reach the value as the Birken-Schumann value, which will be here, right? Because the temperature was written as a stoichiometric temperature plus a perturbation. So when the perturbation is 0, it's the stoichiometric temperature. Temperature will be lower. And that amount is lower by an amount beta -1. Okay, so here, one more thing is that when you look at the form of this problem, there is some symmetry with gamma. In other words, if gamma is positive or negative, if gamma is negative, you can relate it to the solution when gamma is positive. And the relation is by changing gamma to minus gamma and zeta to minus zeta. So this is the symmetry relation. Well, it's important to note, because what this tells you that when you want to solve the problem numerically, it's sufficient to solve it for gamma positive. For gamma negative, you obtain it immediately from there. So, when gamma is positive, what I called S1 will be the fuel leakage. Sorry, and S2 is the oxidizer leakage, and vice versa. Okay, that's what the implication. Okay, those are perhaps detailed, The key thing is that the fuel is related to what I called SF, which is a number which is computed from the boundary value solution, and the oxidizer leakage is obtained from the second relation. So the structure gives us immediately, for a given set of these parameters, gamma and delta, the extent of leakage that you have. Just to tell you perhaps what these two parameters stand for, delta is essentially a reduced Dam-Kohler number. This is the form it takes. It's not strictly proportional to D because it depends here on the amount of, on the enthalpy evaluated at the reaction zone, HF star. Only when the Lewis number are 1, this HF star is 0, and then delta is essentially the Dam-Kohler number. Otherwise, it's modified. Perhaps it's a detail, so I won't spend too much time on further discuss that. Essentially, it's a Dam-Kohler number. And gamma, what is gamma? Gamma is the sum of the two slope divided by the jump. So essentially, it tells you how much more heat is conducted to the left than to the right, okay? And so that's what these two parameters stand for. And here is the solutions for this boundary value problem. And the solution first for gamma equal to 0. Because of the symmetry, gamma equal to 0, everything is symmetric. And so what you see is that if you start for a large value, in other words, when delta goes to infinity, the solution is essentially those two straight lines. Those are like the Birch-Schumann solution. As you reduce delta, so let's say delta equal to 10, you obtain this purple curve. The other one is not shown because it's too far down the scale. Then for delta equal to 2, you obtain this light blue solution, and here is the second one. In other words, there are always two solutions to the problem. Then for delta equal to 1, you get this dark blue. There are two solutions. And then you reduce delta, you obtain the green, and then finally the two collapse, and there is only one solution. And if you try to reduce delta further, there is no solution. So what we find is that the behavior of the structure exhibit essentially something that we would interpret as extinction. In other words, you reduce the Dam-Kohler number, there are two possible solutions, you reduce it further, no solution. Yes? What do the two solutions correspond to? What do they describe? I'm not sure I understood. Say that. So what do the two solutions correspond to? Oh, what are the two? I'll tell you in a few minutes. Yeah. But at the moment, there are two solutions. We're going to interpret that in a second. What happened when you change gamma? So you change it from 0, let's say 0.2, 0.4, 0.6. Well, you see still the same idea. There are two solutions. But now note that there is an asymmetry in those curves, and this tells you something about the leakage. So there is more leakage on one side than on the other, right? Okay, so now let's see what the two solutions represent. So what I have plotted here is the leakage function. Since gamma is positive, is the leakage of the fuel. So what I plotted here is the leakage of the fuel as a function of delta minus the critical delta. So all the critical values are aligned. They, of course, they don't have to be, but I shifted the coordinate to be aligned. So when gamma equal to 0, so here pick up any curve that you like. The two solutions correspond to two possibilities for leakage, a low branch and an upper branch. Obviously, one of them will be unstable, and so clearly, physically, only one would exist. And it's clear which one exists because I anticipate or expect that when delta goes to infinity, the solution will approach the Birch-Schumann solution, and therefore the leakage will go to 0. So what this graph shows is that as you decrease your Dam-Kohler number, there is more and more leakage of fuel through the reaction zone, until delta critical, where the flame can no longer, or reaction can no longer be sustained and extinction occur. If this is the leakage of, this was the leakage of the fuel when gamma is positive, and so this is the leakage of oxidizer. What I want you to know, the difference between the values. There is a significant amount of leakage of fuel, but very, where was I? Here. Very small amount of leakage of oxidizer. When gamma equal to 0, it's a symmetric case. This is those circles, which is, which one is that? It's this black one here, right? And this one is exactly the same as the one here for gamma equal to 1, which is not shown on this scale. I'm sorry, for gamma equal to 0, so it's the blue curve. Okay? So the gamma equal to 0, you obtain the same value, but there is more leakage of fuel when gamma is positive than oxidizer. Okay, so now let's also interpret that in terms of the temperature, which, by the way, we can calculate from knowing the solution by the difference between the stoichiometric, the actual temperature from the stoichiometric temperature. So, so the temperature, as I in fact described before, as part of the S-curve, as you decrease the Dam-Color number, you get two solutions, right? But at some point they coalesce to one. This one is the unstable one, and so when you follow the upper curve, you come to a point where below that value, extinction occurs. So these two solutions describe essentially this part of the S-curve. It doesn't describe the total S-curve because you have to talk about ignition, and I'm not going to discuss it here. Okay, so this was just to remind you a picture that I already discussed earlier, that this is part of this S-curve and describe extinction. One can therefore generalize this idea or write a general formulation, which is the following. If you have a reaction sheet, then the across or the variable at the reaction sheet are continuous. There is a relation between the fluxes, as we interpreted before. The fuel and oxidizer, the fluxes of fuel and oxidizer are in stoichiometric proportion. Similarly, the temperature is related to that. And here is the extent of fuel and oxidizer leakage for given gamma and delta. And gamma and delta in every problem is solved by finding the outer solution, namely the solution outside the sheet. So that eliminates the need, in fact, to every time compute the reaction zone separately. It's done once and for all, if you like. Okay, the next topic that I wanted to, so the key point here that I wanted to emphasize was one, in the previous lecture, we talked about Birch-Schumann solution. I argued that the missing point was to clarify that there is a structure that smooths out the discontinuity. We have seen that that always exists. And when we incorporate the idea of activation energy, we see that it doesn't always exist. It exists only when the Dam-Color number is above a certain value. And that's the important part of this result, that we were able to also identify flame extinction if the Dam-Color number is sufficiently low. The next quick topic that I want to discuss is the mixture fraction formulation. And if we consider two streams, one of fuel that I would call 1 and one of oxidizer that we call 2, then the 1 and 2 appears here as subscript, as you see. Then the mixture fraction is defined as Z, which is more or less one of those coupling functions, more or less just because it is written such that it goes from 0 to 1, 0 on the oxidizer stream and 1 in the fuel stream. But you see it's exactly a difference between YF and YO. So it's this function Z for unity Lewis number should satisfy a reaction-free or it's a conserved scalar, right? And you see why it's 0 on one side and 1 on the other simply by substitution, right? So in the oxidizer stream, there is no fuel, so YF is 0. And what you get is, what do you get? Boom. In the did I write it wrong? In the oxidizer stream, oh, I'm sorry, there is no fuel, so this is 0. YO is YO2, so the difference is 0, right? In the fuel stream, there is no oxidizer, so this is 0. So and the fuel amount is YF1, so you get new YF1 plus YO2. The ratio is 1, so it's correct. Okay? Good. So now just this to show you something that I said in words a minute ago, that Z is a conserved scalar. You see here is the YF equation, YO equation. If you add them up in this way, you get an equation for Z in general of this form, but only when the molecular diffusivity of fuel and oxide is the same does the right-hand side become 0, and then Z is a conserved scalar, and D is the common diffusivity. So Z is an equation that will describe, that you can solve, let's say, a priori, and it describes the mixture fraction in the field. Okay. What is nice about the Z is that if you think of the mass fraction to be function of Z, Z being a function of space and time, then you can see that a solution of the equation is a linear function. In other words, the second derivative of yi with Z is 0, assuming, of course, that Z satisfies this equation. Therefore, yi are a linear function of Z. And if you assume that that Lewis number are 1, also you can show that this other combination, HF and HO, which are also conserved scalar, are also function of Z. So that makes the problem very nicely, but this is good only if the boundary conditions are simple, namely they are constant, because then you can immediately write the solution for YF and YO. So suppose that you are in a frozen situation, right? So no reaction. So YF will be just YF1Z, so that it satisfies it's 1 here and 0 here. I mean, it's YF1 here and 0 here. And YO is YO2 and 1. So on the Z scale, they are simple. But more interesting is, of course, when there is combustion, because then you see there are these profiles, right? They are linear. And Z stoichiometry is the location where the two are consumed. In other words, it's a stoichiometric position, or the stoichiometric. But this in terms of Z, you still have, in principle, to solve Z to find physically where Z is. Okay, so what about the HF and HO? Well, that tells you also the temperature in the Birch-Schumann limit solution is also a linear function of Z, and so here it is. So in terms of the mixture fraction, all the properties are in fact linear, okay? By the way, the flame temperature is given here, okay? It's obtained by equating the top and the bottom relation. The top one was obtained from here by setting that, well, if HF HF is, remember from the previous slide, is a combination of T and fuel. So where there is no fuel, HF is just the temperature. And from this relation, where there is no oxidizer, HO is a temperature. So the HF and HO gives you immediately the temperature field in terms of this mixture fraction. In particular, as I said, the flame temperature is this. And so since we have assumed that the Lewis number are 1 in obtaining this, this must be the adiabatic flame temperature. And it is. It's a little different than what you have seen before simply because I allowed now for T1 and T2 to be different. If you equate T1 and T2, you obtain exactly the previous formula. I didn't write it, but you can verify it. Okay? Okay, so, okay, it's a nice and simple problem where you can solve for Z. For example, suppose that we have to solve, we consider the counterflow problem. So in the counterflow problem, the equation for Z, remember the Z was just convection plus diffusion. So for the counterflow problem, here is convection and diffusion. And that equation admits an exact solution. And so what you have done, you have taken the infinite domain, negative infinity to infinity of the counterflow, and by means of a transformation, you contracted it to a domain 0, 1. That's all what was done, okay? And since now the solution in the Z, the solution, let's forget that for a second. The solution in the Z coordinate, they are linear, but when you replace Z with this error function, you obtain the solution that I derived for you earlier, the error function solution, okay? So maybe it's a transformation, it get simpler to solve some problem. But the idea turned out to be more useful in more complex configuration where the profile depend weakly on the other direction. So people argue that you know, the mixture fraction doesn't vary very much. I mean that the problem depends essentially on the mixture fraction Z. The largest changes, of course, occur where the gradient of Z in the direction of the gradient of Z, because usually along a surface, the gradient is the steepest direction that you proceed. And so if you have, for example, a mixing layer, a fuel coming from here, oxidizer coming from here, these are these were numerically calculated lines of constant Z, okay? Now, for a given situation, let's say Z stoichiometry is some value, so it's one of those Z. So this will be the Z stoichiometry. In other words, for the case I plotted here, this is where the reaction sheet is represented. Now, in this problem, the gradient of Z vary along this like red curve. It doesn't, it's not a constant horizontally. But people are using the idea, just arguing that, you know, we're neglecting those transverse variation and looking only at the variation in grad Z. It's convenient, but it's limited. Another thing is that if you analyze the structure of the reaction zone, okay, as we have done before, then since now the normal is expressed in terms of Z, or the gradient of Z, then the gradient of Z square appear in your structure equation, and of course you can then absorb it into the Damcolor number, and this quantity is often referred to as the instantaneous dissipation rate. So you see the Damcolor number will be related to the dissipation rate, and when the Damcolor number is reduced below a certain value, or the dissipation rate will be increased. If the dissipation rate is above a certain value, extinction occurs. In other words, you can refer the extinction condition to the dissipation rate function. Okay, so I just wanted quickly to bring that idea because it's quite often used in the literature, and it's important to know something about it. The next thing I want to talk is about edge flame, when flame are lifted. And here is a lifted propane air flame. Now I really cheated a little bit because you cannot see in the figure the burner and I put it down here, but this is where more or less it was based on the experiment of Chung and Lee. And so basically this is like a diffusion flame, but the flame does not touch the rim of the burner. In other words, it's lifted above the rim, okay, like this numerical computation show. So what I refer to an edge flame is the structure, this structure in this vicinity. It's a flame that doesn't terminate at a boundary, but has an edge, okay? And that edge, it's quite rich, as we shall see in a moment. Of course, it has practical application because very often you don't want the flame to touch the burner rim, perhaps in order to avoid corrosion or other things. And the other thing is if it's lifted, but you don't want it to be too lifted because it can be blown off easily. On the other hand, lifting the flame provides some mixing here. So what you have, you don't really have a pure diffusion flame. So what you have is a situation like here, for example, where the fuel and oxidizer are coming separately and there is a mixture region here. This is a photograph taken by forcing or forming this edge flame in the laboratory. And the idea is that there is mixing that occur here. So the edge part of the flame is a premix flame. The reason it's curved because the equivalence ratio along the flame is not uniform. At the tip, it's almost stoichiometry. It's a bit rich here because there's more fuel than oxidizer, and it's lean below. And so being lean or rich, it propagates at a lower speed than the stoichiometric surface, and that's why it's retracted to the back, okay? It propagates slower. And so what you have, it's a curved premix flame. But since you have enough fuel coming from here, there is excess fuel that go through the flame, the premix flame, and there is excess oxidizer coming from the other side, and that excess fuel and oxidizer burn here at a diffusion flame. So what you have, it's a structure that has a premix edge with a trailing diffusion flame. Some people call it triple flame. I don't particularly like this term because triple to me, that's one on top of the second on top of the third. And we often use the word tribrachial, which means it has 3 branches. But anyway, whatever you want to call it, it's just a terminology. Yes?
In terms of temperature, the diffusion part will be the hottest, right?
The diffusion is?
Is the hottest part. I mean, in terms of
Well, usually, but yeah. In fact, it's not only the hottest part. What's interesting about this, I don't know if I have a picture of this later on. Remember I told you that the premix flame, the flame temperature doesn't depend on Lewis number. But for a diffusion flame, it does. So what happened when you change the Lewis number from, let's say, high to the lower one would have a higher temperature. So when you change it from, say, a high Lewis number to a low Lewis number, the diffusion flame would have a higher temperature than adiabatic, and it will force the edge also to have a higher temperature because of the heat conducted to it. So even though in principle, a premix flame temperature does not depend, this structure does depend on temperature. I may have that picture, I don't remember. Okay, so to analyze a simple situation of an edge flame, we look at the mixing, at the flow field in the wake of 2 merging streams. So you have a plate, you have 2 boundary layers, the fuel and oxidizer stream may not be the same, and so the boundary layers are not identical, but the thickness of the boundary layer, it's like the reciprocal of the Reynolds number to the 1/2. And then you have a wake here, and the solution usually in the in the wake is often described by what is known as Goldstein similarity solution. Goldstein described that in the, I think in the 50s or so. And, but the problem with Goldstein's solution, I need to flip here a few to remind myself what did I left here. Yeah, okay, so here is the picture. So the boundary layer equations are essentially these, okay? Essentially, in other words, a boundary layer, you eliminate the uyy in the equation, depend only on the axial diffusion. And then these are written in dimensionless form. But note, by the way, that what we have done, since we are focusing on the solution near the axis, so from the boundary layer, we just assume that we are sufficiently close that we take just the slope of the profile, okay? So the slope is A, and we scale the problem with respect to A. So the length scale is going to be the kinematic viscosity nu divided by A square root. The velocity is related to this A. Those are the units. Anyway, I want to move a little fast with this, so to finish on time. And so, this is the problem. And if you look at the Goldstein solution, is essentially is represented by this similarity form, and therefore the equation admit an ODE that can be solved with two boundary conditions, and this is the type of solution that you get for different value of alpha, but I forgot to explain what alpha is. So I'm assuming that the straining here and here is different. So if I scaled with respect to the value A on top, this one will be alpha y. So alpha is how much it's different than the top one. So alpha equal to 1 means the same stream. Alpha equal to 0 means the fuel is coming, oxidizer is 0. Okay, no, okay, so oxidize, okay, no stream in the, okay, so if you see here is the solution, F prime is essentially the axial velocity. So when alpha is 1, it means the velocity, which is the distance here and here, is the same. You have to take, this is as a function of, the profile is drawn as a function of eta. So essentially, this is what you see here, right? This is this profile. That's essentially what's on top. And what's on the bottom, it's the v velocity, which of course, as the two stream merge, then the velocity come, the y component come towards each other, positive, negative, and that's what you see. And that's what you see the variation with alpha. So example, for alpha equal to 0, nothing come from the bottom, everything come from the top. Okay, so this was quick to describe the flow, but the problem with, and I'll skip that, the problem with this flow with Goldstein solution, it has a singularity at the trailing edge of the plate, right? When x goes to 0, become infinite. So a solution is not valid there. In other words, if we look at what's going on, the solution is valid here, but it's not valid near the tip. So near the tip, you have actually the full Navier-Stokes equation to solve. What describes the flow is the full. Some of the resolution of this are related to the so-called triple deck theory in fluid mechanics, and there are different layers that fit into that picture. There was a lot of discussion about this because people wanted to understand what's going on in the wake of a plate. But anyway, for us, the only thing is that we have to concentrate, first of all, on the Navier-Stokes region, because the flame could be attached or close enough to the plate. And later, perhaps when it gets lifted, maybe to fit it in that solution of the Goldstein. Okay, In the following discussion, we have assumed that the flow is solved, but not affected by the flame, because it makes the problem quite complicated numerically. Hopefully in the future, maybe at some point, it will be done. So, so you solve for the flow field, the Navier-Stokes equation, a region like this, and ensure that at large distances, your solution match the Goldstein solution, because we know that that's the correct solution. So this is what was done. These are streamlines for different alpha. Clearly, alpha equal to 1, it's a symmetric situation. Alpha equal to 0.1, it's close to no flow in the oxidizer. In other words, everything is entrained into the mixing layer. Okay? So here it's fully entrained if alpha goes to 0, and then less entrainment, and alpha equal to 1, you have 2 streams. Okay, so the flow accelerates as it goes in, and so we have a solution for the flow field. Now we want to fit a flame to it. So now we want to solve the fuel and the solution for the mass fraction of the fuel and oxidizer, and of course the temperature as well. So that's essentially what the next thing is. And these are typical solutions that you get. You see, they have this structure, this triple edge flame structure, this tribrachial shape, and this is a blown up of this region, okay? This was done for Lewis number equal to 1, phi equal to 1, alpha equal to 1. Alpha equal to 1, the 2 streams are the same. Phi equal to 1, the amount of fuel and oxidizer are in stoichiometric proportion. Lewis number to 1 means the fuel and oxidizer diffuse in the same rate, and so the solution must be symmetric. Indeed it is, okay? It's enough to change one of those for the solution to lose symmetry, so the edge will lean on one side or another, and so on. So you can have a variety of situations. These were reaction rate contour, which clearly show the structure of the flame. This is isotherms. These are isotherms. So it shows you the hot part and so on. As you mentioned before, the hot part is indeed the diffusion flame, and that heats the premixed edge as well. This is just to show you 2 different edges, one which is neither one is symmetric, okay? They are not symmetric, and this one was for a situation where the flow is symmetric, but the edge, you see Lewis number is 0.8, so it's a little leaning off the symmetry line. No, that's not true what I'm saying. Sorry, I apologize. Alpha equal to 1, Lewis number 0.8, I forgot that the calculation here were done with Lewis number of the fuel and oxidizer the same. So if it is the same, Lewis number is 0.8, still means that solution will be symmetric because they diffuse at the temperature will not, but the fuel and oxidizer are. So the solution is symmetric, but this one is not. And this one gain oxygen by entrainment primarily. Well, we couldn't do the limit alpha equal to 0. It's a much more difficult problem, so we got close enough, but up to 0.1. Okay, so, and this is just to show you the temperature, isotherm, mass fraction of the fuel and of the oxidizer. Note, by the way, that the mass fraction of the fuel and oxidizer go past the plate, because we are solving an elliptic problem. We are solving the full. We didn't assume only diffusion. We didn't neglect axial diffusion. So fuel coming out of here may diffuse and find itself a little bit on this side as well. So the integration that we did was from a sufficiently negative value here, which corresponds to sufficiently far ahead of the edge or tip of the plate. And that's the graph actually that I thought I didn't have, but I do have. I asked me before. Here is the flame temperature for different Lewis number. So you see for the Lewis number equal to 1, the flame is adiabatic, and in other words, this is the temperature along the axis. So the temperature rises, the edge is here, the temperature rises, and then it stays at the adiabatic flame temperature. But for a different Lewis number, for on Lewis number less than 1, the temperature is above adiabatic, you get super adiabatic, and the hot diffusion flame heats up also the edge. And for Lewis number larger than 1, you get sub-adiabatic temperature. Okay, temperature is below, and that affects the temperature at the edge. Okay. There would be a difference if the next thing I want to talk about quickly is the position of the edge position relative to the tip of the plate. So now if you have a cold plate, meaning a plate held and at a temperature, constant temperature T0, or whatever the temperature is, what you find is that typically there is a minimum distance that the flame can approach the plate. Otherwise, when you reduce the dam color number, meaning you increase the flow rate, the flame will lift off, right? Position will increase higher and higher. We're going to see in a minute if this is possible or not, under what condition. If the flame was adiabatic, then essentially when D goes to infinity, the flame would be attached to the tip, because what happened when D goes to infinity under a adiabatic condition, immediately the fuel and oxidizer meet, they burn at an infinitely fast rate, so they burn immediately, right? So for infinite dam color number, you expect the flame to be attached, but when the plate is cold, clearly there is heat loss and the flame cannot reach the plate, so it will have to stand off the plate at a certain distance. Now the observation that I want to explain are shown by the experiment of Chung and Lee, and they found that for light fuel like methane, ethane, the diffusion flame remain attached to, more or less, remain attached to the rim, at least as you can observe, and is blown off when you increase the flow rate above a critical value. For the heavier fuel, like propane and butane, the diffusion flame lifts off, stabilizes at significantly distance from the rim, and it will be blown off only if the flow rate is sufficiently large. So we're going to see that those two behaviors are obtained in this calculation, and you see the difference when the Lewis number is 1 or 1.6. The light fuel will correspond to Lewis number 1, the heavier fuel to the large Lewis number. So you see for the Lewis number 1, what you have is a curve that has a turning point here, okay? And this part turned out to be unstable. So you increase the flow rate, the flame get closer and closer and closer. There's always a distance, as I told you before, because the plate is cold. And at that point, there is a turning point, and so if you increase a little bit further, there is no solution, and the flame is extinguished. So this is the blown off in the case of light fuel. Note that the distance here is scaled with respect to the laminar flame thickness, is very small, and so it's practically attached. The difference between the dots here and the dashed dot is that those solutions were obtained by solving Navier-Stokes equation and then the flame position in that solution. And the rest here was assuming the Goldstein similarity solution. In other words, at that distance already you are sufficiently far from the tip, and it seems like Goldstein solution is pretty good. Not only it's pretty good, is that we match it quite well too. Okay, what happens if the fuel is heavy? Well, you reduce you increase the damp color number, you reduce the damp color number by increasing the flow rate, and the flame get closer and closer, and then suddenly it starts lifting off. There is no turning point here. So it lifts off, it lifts off, it lifts off, and it gets stabilized at higher and higher distance as shown experimentally. I will explain to you in a minute what this is, but before that, this is again the solution in the using the Goldstein similarity solution. The point here is that if you use just the similarity solution, you're not really going to obtain the most interesting and critical results that we see, but eventually the solution will fit that. In fact, you're never going to obtain this part because it's all within the Navier-Stokes region. What is this here? Well, between these 2 points, turned out that the flame or the edge tried to stabilize itself, but cannot quite, and start oscillating back and forth. And this is to show that I forgot that I had this. This is to show that I show here 2 values, and this is for a whole other range of values. So the low Lewis number has always a turning point, and the other have no turning point. Okay, so here is the oscillation that I was talking about, and I want you to notice that these 2 points correspond to these 2 points here. So this segment is what I have shown here on the, okay? And what I'm showing here is A, B, C, D, E, and so on are different position. The top one is here, the bottom one is here, and the intermediate one, a few of them are shown. I didn't show all of them. So the top one, you see that the flame, I think it's this value here. Well, let's see. Oh, there is no scale here. But 90, this is 20. Yeah, it should be the top one. So what you see is that when we did a time-dependent calculation, we start with some perturbation of the solution. Solution get perturbed, and then eventually it stabilized to a constant value. So this is the stabilization at this point. When you go to a point here, the solution eventually go to a limit cycle. In other words, the flame just go back and forth, but it's stabilized. So it's another mode of stabilization. Maybe not a one that you prefer, but one that is possible. The same thing as you move, of course, in between there is 2 frequency, 1 frequency, and eventually stabilize again. I'm almost done. We'll take a break. I just want to show you 2 movies. One, when the flame has 1 frequency, you just go back and forth. And the second one, and you have 2 frequencies. Still want to stabilize itself, but it's not blown off, okay? I think this is the end of this. We are going to talk later about a little bit about turbulence and